to do today is to correct a bad mistake I made last time. In fact, I quoted a wrong function giving, well, a wrong name or a wrong function. I mentioned something which is called logistic function or logistic curve. Oh. Nema krede ni jedne.
Ma ima u nekoj učionici blizu sigurno.
Molim?
Ma ima u nekoj učionici pored sigurno.
Aha, da, a to, da. A, dobro.
Moj zna ponekad biti.
Ja, obično bude, jeli? Aha.
Tu dolje ima to kad...
A, evo ga, fina.
Znala sam da mora biti neki.
Da.
Ovo su sve slomljene.
Ništa, to dobre su polovice.
A baš
Puno
sve
hvala,
su slomljene.
hvala, dobro. So now I have a chart here, and I repeat now because there is a new comma. I have to apologize for making a bad mistake last time. You caught me in a mistake. I quoted a wrong function for a logistic curve. Did you? Yes. So thank you, I found. The chart has been found, thank you. And, well, logistic curve. Or function. This is quite an important matter, and I will just consecrate to it a couple of minutes. Not just to correct the error of last time, but to say a bit more. And I'm somehow sorry that I didn't plan to do more about this model. Population growth is the object which is described by such equations. And the most simple model is just the exponential growth. It is connected exponential growth. Which is connected with the name of Malthus, who made a quite terrifying predictions about the growth of the human race. And it is simply that the population P, which is a function of T, grows such that P star or P is some constant R greater than 0, which has a solution P0 e to the RT, exponential growth. That means that the more people you have, the more children you would have, and so on. So, but there is a correction to it, that because there must be, because in the history there was no exponential growth. So something else was working in nature. That means the size of resources so the environment in which you live has an inner limit. And if this limit is denoted by k, then we can correct this equation into p prime over p equals to Lp times 1 minus p over k. That will give the damping, because if p is growing, then the whole thing will be smaller and smaller. Oh no, excuse me. So this gives the differential equation Lp 1 minus p over k. This is a, well, heavily nonlinear equation. And the mathematician who derived it was Veselić. And the equation, the solution is P equals to K over 1 plus K minus P0 over P0 e to the minus RT, where P0 is P, the value, initial value, which is needed for this equation to have a unique solution. How about our theory? We must have we had a theory which could be applied to this equation. Well, you will certainly have a local theory, which is guaranteed by our main theorem we have proved somewhere in the beginning of the course. But to get the behavior, which is quite a fine one, something like that. Well, begins so, and then grows strongly, and then like so, and the same here. See, there is a limit for that. There is a limit for t to minus infinity, where this is 0, and a limit for t to plus infinity, when the whole thing is 0. So this is the x-axis. T to minus, yes, that's it. So if t goes to minus infinity, then this goes to plus infinity, and this goes all together to infinity, so it goes to 0. And the other, and if t goes to plus infinity, then this goes to a constant up there. So now, coming back to our least squares subject, the question is, you have a certain behavior of population, and you would like to check whether it fits to this model. So you will have points, you will measure your population, and then we would like to fit this curve to this data. That would mean fit in the sense of least squares. You have the points x, I, y, I is equal to 1 to n, and you would like to minimize sum over 1 from 1 to n of what? Of k 1 plus k minus p0 e to the minus r, oh, excuse me, ti. Now t is the independent variable, not x. Ti minus xi square minimum. Well, here, this is a non-trivial minimization problem. It has been treated in many many directions, and I will not give any concrete way to solution. What to do? Well, you have software for that. Which software you have for that? This is a smooth minimization problem with no constraints. So you will use what? That's your function. Of what? Of k, r, k and r. Well, that's what it is. You can even add p0. So we have a function of 3 parameters, of 3 variables, and you have to find the minimum. If you had only 2 of them, then you could, of course, try to use Newton method from the very beginning, such that you plot the function. You plot it. It's 2 variables. You can plot it in the plane. And look for such things. Which boils down to make a function table just in an old tables of functions and look for a minimum in a finite set. But this grows approximate minimum then. And then to start Newton method from this in the hope that it will converge fast. This can be done in 2 variables. In 3 and more, it grows exponentially. So you must look for some different ways for starting approximation, because you know that Newton will converge only if you are close enough. But that's not all. The problem is there may be more local minima. If it were mechanics, then each of those minima would give you what? The equilibrium position. But in this case, no. In this case, you would like to find the absolute minimum, because you would like to fit as good as possible. So I have to choose between the two. Usually, I tried myself once, just to look how it works. You have you have D of F and you have D2 of F. Those two objects will be used in the computation. So if you start somewhere and you see that your Hessian is indefinite, that's not a good starting point for a minimum. What you can do is forget about D2F and just work with the gradient. Why? Well, if gradient is not 0, then you take the negative value, negative direction of the gradient, and the function will decrease for a while. And what you can do is take the gradient somewhere, like for example here. So the gradient be that. So you now take this line and minimize the function over this line. This is now a one-dimensional problem. And then start again. Look at the second derivatives. Did they become positive? And as soon as you can, switch to Newton, because this gradient method is very slow. So this is what you can do, and in fact, many methods which are in the software don't use anything better than that. There are some more sophisticated things, but the big deal is the so-called software engineering. That's not just the mathematics. So because in every step you have to solve a system of equations. If the number of parameters is large, then it will become very soon prohibitive. So that much about such problems. In this or similar cases, you will usually have a small number of parameters, here 2 or 3. But then you will be asked to do a very accurate minimization because of the importance of the problem. So that much about you see. Let me just make one more observation. Well, let me call the variable here x. So KLP will be x. So we use the formula, which is equal to xn minus d2f xn minus 1 dfxn. That's Newton. But in looking at this, we have to solve the linear system of linear equations, in fact, such that xn plus 1 minus xn d2fxn is equal to dfxn. That's the step you have to do to solve the system of linear equations. This is a symmetric matrix, okay? Must be. But we know that we look for places where it is not just symmetric, but positive definite. And you can check for positive definiteness in the course of solving this equation. Gaussian elimination would tell you at once the system is not definite if it emits a negative element on the diagonal. So now you can stop Newton and go to a more secure gradient method. So these are details of computation I just met myself. Because if you compute for too long time in the wrong direction, that's not a good method. These are just some details on this computation. In my book, Veselić, Matematičke metode I modeli, mathematical methods and models. You will have a demonstration of the Newton process in this sense to the problem of two springs, which I have discussed with you, where also a picture of this kind is displayed. So you may look into it a bit to look how the things can behave in a very concrete situation. And in this case, you will indeed have many, not just one minimum position, but I think two. In my opinion, solving such a system for at least two variables should be a compulsory exercise for everybody who studies mathematics. You must experience it somehow. And you see how the theory helps you, but only for some basis. After that, you are left to what? Well, to your skill and to your experience. Almost every model I showed you had this problem, that the theory helps you a great deal, but it doesn't give you the final answer in the concrete situation. And that's the life. So, okay. Now, as I promised, my last topic, which will cover this morning and next Monday, will be abbreviated with CT, meaning computing, somebody say computerized tomography. Well, physically, this is just a sort of improved X-ray diagnostics. We all know from the dentist or pulmonology or everything else. If you break your bone, then you go to X-ray to look what it is. So what you have, you have X-rays going through a body, losing their intensity according to the density of the body. So that the intensity here will be a function, well, if we are in the plane, of this one variable. So let me just make it the picture this way. And if you are in the space, then it will be a function of two variables in a plane. What you see. So according to this, you can, just by seeing, recognize the elements of the body. In more sophisticated apparatus, you can be rotated. I myself experienced it when I had to be looked at the stomach, and I was bound to the device and rotated in the place upside down almost. Yes. So what's the aim of this? The aim is that if you take many directions, you will get a better information. And who assembled this information? It was the eye and the mind of the doctor who did that, and his experience. He knew what happens if he rotates you and so on. Now, computing tomography is perfectioning all these things. You are put into a tunnel and the sources of the X-rays are rotating themselves many times. That's the first. You have enriched your data. And the second is the computer treatment, processing of them, which is much more accurate than the human eye. So these two elements. So all directions and computer processing. This makes the diagnosis much more reliable. And the matter itself has experienced a huge growth in research. I can only just make an outline. I will not prove many things because they are difficult. I will just describe them. And then at the end, I will also add some primitive numerical methods to let you look and experience for yourself. So, So we will now restrict ourselves to two-dimensional model. That means everything is happening in a fixed plane, and your body is a region in the plane. Body is a region in the plane. When I say a region, that it is not just a subset, but a bit more than that. It's usually something which is mostly convex, open, and so on. That's what defines usually by the word region. And the body is characterized not only by its size, but by the so-called attenuation function. Attenuation. Some people say absorption for that function. Absorption. That is the quality of the material to attenuate the ray coming through it. In which sense? Well, first, the law of absorbing. That means, first of all, the direction of the ray is not changed. Only its intensity is changed. So if I denote it the intensity, that's amplitude of whatever you wish of a ray on a certain line. Then the fundamental law of absorption reads the change of the density is minus f of x times I times delta s. So I have here a small piece of line, which is delta s. S is just measuring the distance on the line. So it is proportional, of course, to the length, and it is proportional also to the intensity itself. And it's negative, it is loss of the intensity. If delta S is very small, then this is approximated by the derivative. Of course, your x is connected with s. Linearly. A simple special case is f is constant whatsoever. So that means that the material is homogeneous. Then this has a simple solution. Otherwise, we have a simple differential equation. Now let me specify what this means. This means f, I have to specify how x depends on s. It is a line, straight line, equation of a line, nothing else. And I have now to specify the form of the equation of a line. There are many forms of it. I will choose the following representation. This is my line. This is my omega. And this is perpendicular. This is phi. And this is the unit vector in this direction, which I will call theta, and another vector orthogonal to it will be called theta perpendicular. Now with those parameters, if I now call this P and this, if I have a point here, that's my x of s, then this x of s will be equal to P theta plus s theta perpendicular. So I have here minus f p theta plus s theta perpendicular times I. Now, this is now a bona fide differential equation. But p is fixed and s is varying. And this equation has a simple solution. This is a linear equation of first order with variable coefficients. And solution is, as every student of calculus knows or should know, where S0 is determined by the initial conditions. So now, which will be the natural way of defining this initial condition? we will take the function f to have a compact support. Then I don't need to define my region anymore, because where the function is 0, that's now the limit of the body. Well, usually the function will be continuous, but this may also be a bit different, because the more discontinuous this function is, the more it interests us, because that would mean strong changes in the density in the body, where disease can be. So this is a quite important point. But we start with smooth functions, and and hope that density argument will cover everything else. You see, when you're doing things like differential equations or Fourier transform, your first formula they define for with smooth functions, and then you extend it just like the integrals. First on continuous functions, and then you got up, and in fact nothing changes. So, yes. If you take now the intensity here outside to be E in, on outside E out, then we will have I in over I out to be equal as e to the integral now over all r f p theta plus s theta t ds. And we would like somehow from these quantities here, which now depend on p and phi, because don't forget, theta is theta phi is equal to cosinus phi minus phi, and equal to minus. So this quotient will be function of p and phi. That's for each line one result. And out of those, as a function of p and phi, I would like to determine my f. That's the idea. Now, knowing this, only its logarithm is the same thing. So if taking now ln of I out over I in, and denoting this by g of p and of phi f p, then this will be this now is now the equation. This is the equation, and it's our task to find in which way this equation is solvable, and then maybe also something about the properties of the solution. Because you know that before you start numerics, you must be armed with a good deal of theoretical knowledge of this equation. Stability, correctness, and so on. Yes. I think I did it. Out. Yes, yes, yes. The sign should be correct. I out, I in, out. Yeah, that's it, yes. And you have here a minus sign. It is just changing the sign. And that's what you call your G. So, in the next hour, we will derive some properties of this equation, which carries the name of radon. Integral which was invented by the Austrian mathematician Radon completely independently of any application. As it very often is the case in mathematics. The model, I mean the theory has been done out of nothing just by the interest of a mathematician playing. And then after that, the application was found. That's not the first time. Probably the most notorious case is how the Heisenberg rediscovered matrices because he didn't know anything about them. how poor was mathematical knowledge. And then in traveling in a train with a colleague mathematician, telling him about that, and he said, well, but it's matrices. Well, and that's not the only quite few of such important paramount cases where the theory was developed before. Just think of Ricci tensors, which now led to the proof of the Poincaré hypothesis. Ricci tensors were sleeping in some buried paper till Einstein again rediscovered them, and then some people said that's what it is. So, okay. So, quarter of an hour. Mm-hmm.